Good morning, ladies and gentlemen. I welcome you all to the first session of the second day of our e-conference. First of all, we have the privilege to hear from our keynote speaker, Professor Mohammad Sajid. Professor Mohammad Sajid is presently serving at the Department of Mathematics and Statistics, International Islamic University, Islamabad. Previously, he has served as the chairperson of the department. His field of research is fluid mechanics. Moreover, he has an excellent academic as well as research profile, and with a tremendous contribution in terms of publications and impact factor. The title of his talk is Non-Newtonian Fluid Models in Polymer Processing. So I would request Professor Mohammad Sajid to please begin his presentation.
Thank you, Miraj, for your introduction. Let me share my screen. Are you getting my screen?
Yes.
Okay. First of all, I like to thank you, thank the organizing committee, particularly the chairperson of the mathematics department at NUST, Dr. Miraj Mustafa Hashmi, for providing me this opportunity to speak to the audience that are from multiple disciplines in mathematics. The title of the talk, which I'm going to present today, is the non-Newtonian fluid models in polymer processing. There are two basic objectives of this talk. Because the audience is from multiple disciplines, therefore I thought that I should be explaining the details of the processes in the polymer industry in the first, and then I will also explain the details of the constitutive equations related to different non-Newtonian models. Then I will take a particular example to discuss the details of the problem I have considered for this presentation. The second important thing is the mathematical models that can be developed to explain or elaborate or analyze the mechanism in the polymer processing. And they can be used to predict some important parameters of engineering interest. Our purpose here is to expose the research students with the mathematical modeling of such situations. I have divided the presentation into three major parts. In the first part, I will be briefly explaining the polymer processes in the industries. And in the second part, I will be explaining the mathematical models based on the physical laws and the constitutive relationships of the non-Newtonian fluids and the related boundary conditions of the problem. And in the third part of the presentation, I will be taking a particular example of the calendaring process in the polymer industry. And I will use the constitutive equation of a FINEP fluid to describe the theoretical results and the predictions for the engineers who are working in this industry related to these processes. First of all, the polymer processing is defined as the engineering activity that is concerned with operations that are carried out in polymeric materials or systems to increase their utility. Industries associated with polymeric materials either concerned with the production of the polymers from raw material or with the physical conversion of polymeric material with the finished product. Mathematical modeling plays a central role in the process development and design of such processes. And there are several important polymer processing operations, such as wire coating, calendaring, roll coating, spin coating, knife coating, die forming, and mold coating. So there are multiple procedures. To explain the audience, particularly the research students, I will be briefly explaining a hypothetical model that will explain the different processes in the polymer industry, how one can make a sheet of the desired thickness, or how one can formulate a plastic film or to coat a sheet. So let us consider a flow sheet of a hypothetical process for making a plastic film. The steps are, for example, one can start from the first step is the dissolution. It means that the polymer in the form of a solid is mixed with a solvent to form a liquid, and that liquid is then transported from one place to the other through the process of pumping. Then there is a possibility of having more than two liquids, and in such a case we need to mix those liquids and to properties and to make sure that what kind of properties we have to attain for the mixing of such liquids, how to define mixedness, properties that needs to be considered for mixing are considered in this step. Then the next step is the extrusion. Extrusion is basically a pump that is used for the melting and mixing of the liquid that is coming into the die. Then we pass through this liquid through a die, and this die is designed to ensure the film thickness, temperature, stress level, linear speed, and such other properties. And then the liquid in the form of a film is passed through a colander. Colander is basically a process I will explain in the next slide as well, that it is a process of making a sheet of desired thickness, as well as it is the process of coating a layer of a liquid on a substrate as well. So after the colandering process, there is a process known as drying, which is basically the process of the stretching of the film between the two rolls. Then the next process is the coating, and for coating one can use the blade coating process, the roll coating process, or knife coating, whatsoever. So there are different mechanisms of coating a liquid on a film. Then, because the coating material involves the solvent, and then one needs to exclude that solvent from the coating material, and for this process the drying procedure is used. On the basis of the temperature variations, one can dry the film that is produced over a substrate. And not all these processes are get into the mathematical model, because these processes are involved in the industry. But for mathematical modeling, we usually use the process of calendaring. We use the mathematical models to describe the process of calendaring, and we use the mathematical models to describe the process of coating. So there are two main processes in whole of this activity that is related to the mathematical models, and those are the calendaring and coating. So I will be briefly explaining the few of them the next coming slides. For example, because I am explaining a particular example in the forthcoming slides for the process of calendaring of a non-Newtonian fluid. Therefore, I will be briefly explaining what basically calendaring means. The mechanism of producing a sheet of desired thickness by dragging a molten polymer through a narrow gap between two co-rotating rolls. You can also see it from the diagram on the right hand side of the slide, that there are two co-rotating rolls and rotating in the opposite direction. One is in the clockwise and the other one is anti-clockwise, and a liquid is coming and a sheet of desired thickness is produced. We develop a mathematical model in the next slides for this particular process. This mechanism is commonly used in paper, plastic, rubber, and steel industries. Then there is another process known as the roll coating. Roll coating is a process in which a liquid is applied over a moving sheet or web for the sake of producing a thin, uniform layer of fluid onto the sheet. For example, you can see from this figure, this is an uncoated web, and this is basically the polymer solution that is coming, and we need to film this sheet with this liquid. And this is the second roll, which is basically also playing the cooling or heating process into it, so that the this liquid is coated onto this web, and the coated web is collected on this side of the word web is frequently used in coating process to denote the sheet which has to be coated. Then there is another process of the wire coating, which is very common, that in wire coating operation, the extruded polymer is continuously pumped over a preheated bare wire, axially moving through a die, or the wire is dragged with a constant speed through the extruded polymer. You can see that the polymer is collected into the die, and this wire is dragged through the liquid, and this liquid is coated on the wire. Another mechanism of the coating is known as the blade coating. The blade coating is a processing method for the fabrication of large area films or rigid or flexible substrates. For large scale processing, the blade is moved over a flat surface. Sorry, for lab scale processing, the blade is moved over a flat surface, and for large scale processes, the blade is fixed over the moving substrate. You can see that this blade is fixed over here, the liquid is coming into it, and this is the substrate which is to be coated with this polymeric liquid. So the sheet is moved like this, and this liquid is coated with the definitely there are temperature properties and the mechanism over there. Now the explained steps, the many of these steps refer to the transport phenomena, the process of momentum, heat, and mass transfer. And fluid dynamics is basically associated with the momentum transfer. So this forces us to look fluid flow models for such situations. Because I have already explained, there are two main situations: the process of calendering and the process of coating that is used to be mathematically modeled through the fluid mechanics equations. So any model in the fluid mechanics can be based on the physical laws of the conservation of mass, the conservation of linear momentum, the conservation of angular momentum, the first law of thermodynamics, and the second law of thermodynamics. Only these first two basic laws are necessary for a minimum level of study of any fluid problem: the conservation of mass and the conservation of momentum. If there are rotations involved into the system, then we need to add the angular momentum terms, and if there is the involvement of the heat transfer, then we need to also incorporate the first law of thermodynamics and the second law of thermodynamics. And it is not necessary that we use all these laws together, but there are some situations where we also need the additional features. For example, if you have a situation in which the fluid is moving through a magnetic field, then we need to incorporate as well the Lorentz force into the momentum equation. And if the fluid is moving through the porous medium, then we have to incorporate the Darcy resistance. So there are additional features coming into the equations if we have additional restrictions onto the problem. And since once we have developed a mathematical model in the form of partial differential equations, then a question arises that how to simplify this model or how to solve this model. So many apparently simple problems in fluid mechanics that cannot be solved analytically, and in such situations we must resort to more complicated numerical solutions and results of the experimental tests. The fundamental governing equations that are needed to be used for the discussion of a fluid model, the continuity equation which is given in this equation, and the equation which relates to the conservation of the momentum known as the equation of motion. Then if there is heat transfer, then the conservation of energy equation is also over there, and this d by dt is basically the convective derivative. So this is given over here through this expression. So these are basically three fundamental equations that are necessary to be solved for analyzing any fluid model. In these equations, you see that there is a stress tensor tau over here. So this stress tensor tau is related to the deformation rate in many ways. So the subject that deals with it is known as the rheology. So we have to establish that what the liquid we are using to describe any fluid model, we need to have a constitutive relationship that relates the shear stress with the deformation rate for that particular fluid, or which is near to that particular fluid, that which can predict the properties of that particular fluid. So we need to define that which kind of constitutive relationship we are going to use to study our fluid model. So the subject that deals with such situation is known as rheology, and it is the study of relationships between stress and corresponding strain in a non-rigid substance. The first rheological law is given by Hooks in 1676, that states that the deformation is proportional to the applied force, and fluids for which this is for the solids, and for the fluids, for the first time the law is given by the Newton, which is the fluids for which the shearing stress is linearly related to the rate of shearing strain are designated as Newtonian fluids, and this model was given by Newton in 1686. Most common fluids such as water, air, and gasoline are Newtonian under normal conditions. Maxwell in 1867 suggested that all substances, including gases, should possess both viscosity and elasticity in shear. And the glue, he quoted an example of the glue. The glue exhibited a time-delayed partial recovery of deformation, and this was the first recorded observation of a non-Newtonian behavior that deviates from the Newton's law of viscosity. And fluids for which the shearing stress is not linearly related to the rate of shearing strain are designated as non-Newtonian fluids. And in late 1920s, it became realized that there exist large variations in non-Newtonian behavior, and therefore one cannot describe all non-Newtonian liquids by a single constitutive relationship. So because there are complex nature of such fluids, so one cannot demonstrate or describe the properties of all non-Newtonian fluids on the basis of a single constitutive equation. So there exists a rheological classification. One can define different classes of such non-Newtonian fluids: the time-independent fluids, the thixotropic fluids, viscoelastic fluids linear, and viscoelastic fluids non-linear. So these classifications exist for the non-Newtonian fluids. I will briefly explain the time-independent fluids, and they further divided into three categories. The pseudoplastic are famously known as shear thinning fluids, the dilatant are shear thickening fluids, and the viscoplastic fluids. Shear thinning fluids mean when we increase the rate of shear, the viscosity decreases, and the opposite behavior is shear thickening, that by increasing the shear, the viscosity increases. And viscoplastic is the behavior of the fluid in which fluid needs a minimum amount of stress to be moved, which is known as the yield stress. For example, the toothpaste and like these type of fluids are fall in the category of the viscoplastic fluids. Thixotropic fluids are those fluids whose present sheared internal structure is undergoing change for any reason. For example, gel that becomes thin on shearing and viscosity decreases with time. The opposite type of behavior, namely a built-up of structure under steady shearing motion, is known as rheopaxy or anti-thixotropy. In this case, structure builds up and viscosity increases with time, and fluids even solidify in some cases. The other very important class of non-Newtonian fluids is known as the viscoelastic fluids, and there are two models related to the viscoelastic fluids. One is the linear model, and the second one is the non-linear model. This is a type which possesses both appreciable elasticity of shape and also viscous properties. In oscillatory shearing motion, elasticity produces a lag between the shear rate and stress. This phenomena occurs when applied shear stress is small or slow. And for nonlinear case, if the shear is large enough, then the strong elastic liquids show normal stress effects, and the normal stresses on the face of an elemental cube are no longer equal. So in the different directions, the normal stress effects are different. Another important class of the non-Newtonian fluids is the generalized Newtonian fluid, which is based on the experimental data. The people have predicted some fluid models on the basis of the empirical results based on the experimental data. So in such cases, the important phenomena in the generalized Newtonian fluid is that the shear stress is a function of shear rate at a particular time, but not dependent upon the history of the deformation, that the previous state of deformation does not affect the present state of deformation. The constitutive equation for such fluids is the generalized form of the Newtonian fluid. The power law, the Caro cross fluid are examples of such fluid. And in such case, one can express the stress tensor in the form of a Newtonian fluid, where this gamma dot is the first Rivlin-Eriksson tensor. This mu effective is basically the apparent viscosity. And this gamma dot is the second invariant of the first Rivlin-Eriksson tensor. The other class is the differential type fluids. As we have already mentioned in the generalized Newtonian case, that the current state of the deformation does not depend on the history of the deformation, but in the differential type fluid, the current state of the deformation depends on the history of the deformation. So for a short part, the recent memory is very important in such fluid. More specifically, stress is a function of the velocity gradient and some number of its higher derivatives. These materials lack a gradually fading memory. Instead, their memory fades precipitously, that it fades suddenly. Further, they do not exhibit stress relaxation in a creeping flow. Second grade, third grade, and fourth grade fluid models are the examples of differential type fluids. Another important class of fluid, non-Newtonian fluids, is the rate type fluids. And this is because of the Maxwell, who put forward a mathematical model in 1866 that describes the elastic and viscous behavior of gases. He recognized the notion of stress relaxation and introduced the concept of time relaxation. Oldroyd was first to develop the rheological framework for rate type fluids. The important thing is that in differential type fluids, stress is explicitly given in terms of velocity gradients and its higher derivatives. However, in rate type fluids, this relation is implicit, and sometimes it is difficult. We need not to solve the fundamental equations, but also to solve the partial differential equations that are describing the constitutive relationship. Once we have the fundamental equation and we have the constitutive relationship in hand, then we need to impose the physical boundary conditions based on the interaction of the fluid either with the solid interface or with the fluid interface. So when we are dealing with the fluid solid interface, we have to incorporate in some cases the no slip boundary condition or the slip boundary condition or the generalized slip boundary condition. I'm not into going into the detail of these boundary conditions. And if we are dealing with the fluid interface, we need to stress on the continuity of the velocity and the shear stress at the fluid interface. Now, coming to the particular example of the process of calendaring of a FINAP fluid, first I will describe the fundamental equations that are necessary for solving this. The first two basic equations are the continuity equation, and this is the continuity equation for an incompressible fluid. The second one is the equation of motion. Here, this tau is the stress tensor, which for a FINAP fluid is related to the deformation tensor through this relation, where this tau triangle is the notation for a derivative, and this derivative is described this is the upper convective material derivative, and this is described with this relation, and this f over here is basically the function of the trace of tau, which is the first invariant of the stress tensor. And this is described over here, where these a, lambda f, eta p, and L square are the parameters that are of the FINAP fluid. If I further explain the process of calendaring through the geometry of the problem, so you can see that because the calendaring process is basically a process in which a film of desired thickness is produced, when it is passes through the two co-rotating cylinders. So consider two co-rotating cylinders of the radius capital R, and they are rotating with a velocity capital U. And you can also see that this is the narrow gap between two co-rotating cylinders, which have the width h naught, and a liquid having the width hf, 2hf basically, is coming inside, and it interacts the rolls at a point minus xf. Then it is moving inside with a velocity, and when there is a position x naught where we say that this liquid leaves the rolls, and the sheet of the thickness 2h is produced during this process. So one can control this width of the sheet that is produced through this process. So the boundary of this rotating cylinder is given by this expression over here. And since we have assumed that this narrow gap is much smaller than the radius of this rotating cylinder, so in such a case the lubrication approximation theory comes into play, and that significantly simplify the mathematical model that we are dealing with for such kind of situation. So if I put a mathematical model for a two-dimensional flow, because this is a situation in which the velocity field depends on the x and y coordinates. So the mathematical model will be based on a two-dimensional flow model. And so the velocity field is like this. The continuity equation for incompressible fluid turns out to be this. And these are basically two momentum equations in which the shear stress tau xx and tau xy and tau yy, these three terms of the shear stress, are calculated from the constitutive relationship given over here for the Finopi fluid. So for this constitutive relationship, when we pin this velocity field into those equations, we get this additional equation 1, 2, 3, and 4. These four additional equations are basically coming from the relation of the constitutive relation of the fluid given by this equation. So now you can see that this is an implicit relation. So we need to solve these. There are two unknowns u and v, and third unknown is the pressure P. Then there are three unknowns, tau xx, tau xy, and tau yy. So there are 6 unknowns, and we have 6 equations, partial differential equations to solve. So this is a difficult system to be solved in its present form. So we utilize the condition that the gap between the two rolls is much smaller than the radius of the roll. So by incorporating this condition, which is a physical condition in this case, and which is famously known as the lubrication approximation theory in fluid mechanics. So, and assuming a creeping flow, because in such situations where polymer is moving, the flow is moving very slowly, and in such cases the inertial part can be neglected. So we have neglected the inertial part, and we further assume that this v is much less than u, and the partial derivatives in the direction of x are much smaller than the partial derivatives in the direction of y. These are all the assumptions of the lubrication theory. And once we utilize these assumptions into these equations considerably simplify for us, and we get that the pressure is not a function of y in such a case. And we can easily now solve this equation by integrating this equation. We can determine the tau xy component from here. And further, because the situation of this diagram shows us that the flow is symmetric in the upper half part and in the lower half part, so we can also utilize the symmetry property. So the symmetry property says that the shear stress is 0 at the center line. And also we have that at the interface where the fluids interact with the roll, that is y bar is equal to h of x bar, then the velocity of the fluid and the roll coincides. And introducing the following dimensionless variables, we come to the dimensionless form of the system of partial differential equation. And we need to solve this system. From here, we can integrate this system once. and after integrating we get the value of tau xy. We can substitute this value of tau xy into this expression of f and into this equation, and integrating once we can find the value of u. And we can also transform this into a variable so that we can draw our graphs between 0 and 1. So by taking this transformation, in the velocity in the new variable can be expressed in this form. On the basis of this velocity, because in these situations pressure is not known to us, but the flow rate of the situation is given to us, that the fluid is moving with this rate. And so by utilizing the formula for the flow rate, because this flow rate is known to us, we can find the flow rate and we can find the pressure gradient from here. And by integrating this pressure gradient, we can find out the value of the pressure. We can find out the quantities of engineering interest, like the roll separating force, that when the fluid is leaving the rolls, what is the force on it. Then we can also find out the power transmitted on the roll. We can also find out the shear viscosity, and we can also find out the first normal stress coefficient. So these are the expressions for finding these values. So once we have calculated all these values, then we can draw some results on the basis of these values. This is basically the description of the shear viscosity for various value of the extensibility parameter and the Deborah number. And these are results for the first normal stress coefficients, and these are the velocity profiles. This is at the position where the fluid is entering into the colander, and this is the situation when the fluid is leaving the colander at the point x is equal to x naught. These are basically the profiles for the pressure gradient, and you can see that these are starting from different points, because the entry point is different for different situations of the pressure. And these are the profiles of the pressure, and these are basically the leave of distance, the thickness of the sheet, and this is the force function, that is force required, and this is the power we have plotted here. And we have some key findings related to this study. I have not explained in detail the mathematical, because it's somehow a complicated model and you need to solve it. Then the key findings of the present study are basically the pressure inside the colander decreases by increasing the viscoelasticity of the fluid. Then the thickness of the exiting sheet is less for viscoelastic fluids up to a specific value of entering sheet thickness, and then it increases. Because we are comparing our results with the theoretical model of the Newtonian fluid already exists in the book of Stanley Middleman on the fundamentals of polymer processing. And we observed that a reduction of about 55% is noted in the roll separating force when Deborah number increases from 0 to 10, and the power transmitted to the fluid by the rolls is 68% roughly less than its Newtonian value. And these results are already published in the Journal of Non-Newtonian Fluid Mechanics. And if someone is interested in the details of the calculation, one can also go through this research publication. And we are hopeful that the solution presented here provides a solid benchmark for the computational modeling of the more sophisticated two-dimensional calendaring problems. I also like to explain that I was associated as the adjunct faculty in NUST as well in 2016, and I supervised two MPhil students. One of them have worked on such kind of problem, and we investigated a flow, this problem of some authors from Sweden, and we pointed out some corrections in their model to the authors, and they have corrected their, and they acknowledged the efforts of this, and they have also acknowledged the School of Natural Sciences, National University of Science and Technology, because the student Hira Siddiq was a MPhil student over there in the department. I was supervising her case, and she also published a paper from the School of Natural Sciences address in another fluid model. Thank you very much for your attentions. Questions are welcome.
Okay.
Yes. Any questions, please?
So thank you, Dr. Sajid, Professor Sajid, for a very nice talk. So now we are going to have a question answer session, and participants as well as panelists are encouraged to ask questions if they have. Dr. Asif, can you figure out if there is any hand raise?
No, there is no hand raise up to this point.
Okay, so I have a question, Professor Sajid.
Yes, welcome, please.
Yeah. If we see the model of the calendaring that we have shown us earlier, it involved two cylinders.
Yeah.
And between the two cylinders there was fluid. So, and I just thought that wouldn't it be appropriate if we deal with the cylindrical coordinate system in this case? Rather, we preferred a Cartesian coordinate system.
Yeah, you are right that, but the assumption we have taken over for simplification of our equations is that the radius of the cylinder is much larger than the narrow gap produced between the, because the thickness desired by the sheet, because we have shown in the diagram, you can see that this gap is much larger, looking very larger, but in the real situation, this gap is very narrow, maybe in millimeters. And when it compared to the radius of the cylinders, then the curvature effects are negligible. Because the x naught over r term is much smaller than 1. So since the curvature effects are negligible, so for the purpose of the mathematical model, we cannot use the cylindrical coordinates, and the mathematical model based on the Cartesian coordinate is sufficient to predict the correct things, because in one of our other paper, we have compared our results with the experimental available data, and we found a very good comparison of those results. And therefore, and also the same was demonstrated in the fundamental book on the mathematical models of polymer processing by Stanley Middleman, and they have used the same mathematical coordinates for describing such situation.
Okay, sir, one quick question related to to my previous question. So if you can please show us page 23 of your PDF.
Okay, fine. Yes, please.
Sir, so if looking at this picture, the diagram, it seems that this capital U is the tangential velocity.
This capital U is the velocity of the roll. This is the angular velocity. Yeah.
So, sir, if this is the angular velocity, then if we want to calculate the tangential velocity, it should be multiplied with the radius, and then the velocity, the tangential velocity should be from the formula V is equal to R omega. We should get it U multiplied by the radius of the cylinder. So the contribution of R should be here. And looking at the boundary conditions that at page 27, if you can go, sir, please. So, yeah. So we have U is equal to capital U. U bar is equal to capital U at Y is equal to H of X bar. So I was just wondering that one should have this radius multiplied with the capital U if in case, if we are saying that it is the angular velocity. If it is tangential velocity, it is okay. So
basically the answer lies in the previous discussion as well, because because the mathematical model is for the narrow gap, and in the narrow gap the situation, the curvature is negligible, and in that particular situation one can utilize the capital U velocity as compared with the U. But your point is very valid, and I will look into the possibility of putting R into the mathematical model and see what effects will be seen, because I have not yet seen it, but I will take your point very seriously, and we can develop a mathematical model by taking into that radius R into the equation, and then I can be able to say something about the whether we get some different scenario or the similar things what we have already got.
Okay, sir. So thank you so much for a very nice presentation. And I must appreciate the basics that were actually covered during the talk. And those basics are often ignored in the fluid dynamics lectures. So we would certainly appreciate that. Thank you so much,
because
sir.
I have used those for because there is audience of from multiple disciplines, so I thought that some of the audience may be interested in the basics. Yeah, thank you.
Right. Okay, so our next speaker is Dr. Yusuf Habib from ComSets University, Lahore. He is the expert in numerical analysis, and he is also the ex-faculty member of our NUST School of Natural Sciences. So we have the privilege to hear from you. Now, Dr. Yusuf Habib will speak on the numerical treatment of conservative differential equations. So, Dr. Yusuf, you can please, yes. Yes.
I hope you can
Yes.
see me and you can hear me as well.
Yes.
Okay. First of all, I would like to thank the organizers of this conference, who are my colleague, who were my colleagues and who are friends to me as well, for inviting me to such a nice conference. It's an e-conference and it's a good initiative, and I must appreciate it. And I'm very happy to be part of this conference, actually. Okay, so my presentation is, I'll just share it. Just 1 minute. So I hope you can see this share screen now, right?
Yes, it is visible.
Okay, so good. The title of my talk is The Numerical Treatment of Conservative Differential Equations. The outline of the talk is, in the beginning, I will talk about geometric numerical integration. Then I will talk about partitioned Runge-Kutta methods. Then I will talk about order conditions of partitioned Runge-Kutta methods. Then I will talk about the new kind of methods. They are called effective order methods, and I will discuss about effective order conditions. Then the new methods which we have discovered, I will talk about them. And then in the end, we have extended this effective order partition Runge-Kutta methods to solve the Hamiltonian system, which are the conservative differential equations. And such methods are the symplectic effective order partition methods. Geometric numerical integration. So basically, geometric numerical integration is a branch of numerical analysis. And this branch is concerned with the preservation of geometric and physical properties of a differential equation after discretization. With this, I mean that if you have a differential equation and you have some certain conserved quantities, we want our conserved quantities to be preserved numerically as well. That means, for example, conservation of energy, conservation of momentum, they are preserved analytically. But we want to make sure that our numerical analysis and numerical method preserves the energy or the momentum or the phase space or the symmetry of the differential equation numerically as well. And this branch is known as the geometric numerical integration. So for the Hamiltonian system, we have symplectic methods. So for reversible system, we have symmetric methods. For differential equation on manifolds, we have Lie group integrators. And for integral preserving equations, we have discrete gradient method. So What are conservative differential equations? Well, the concept of first integral. So if we are given a differential equation y dash is equal to f of y, then a function h of y is the first integral if it satisfies the equation such that the gradient of h multiplied by the right hand side of the differential equation will yield a zero answer. So for harmonic oscillator, it's a Hamiltonian system, and the P dash is minus Q and Q dash is P. These are the generalized coordinates and generalized momenta of the harmonic oscillator. It can be a mass spring system, a mass attached to a spring going back and forth. And it has a quadratic first integral. H is P squared over 2 plus Q squared over 2. And this is a conserved thing. That means the H will not change. And this is particularly interesting because if we put initial condition in it, let's say if I put P naught as 1 and Q naught as 1, so this means that answer of H should be 1 by 2 plus 1 by 2, and which is equal to 1. That means this energy of the system remains same. The 1 remains same throughout the process. And we want to make sure that, and this is the first integral as well, we can check it, that a gradient of h multiplied by the right hand side of the differential equation, f of y, and we get answer 0. What is our aim? Our aim is we want to numerically solve this differential equation with initial condition, and we will obtain discrete solutions. Obviously, it's a discretization, so we will not get the continuous solution. We will get the discrete solutions, y0, y1, y2, y3, yn, whatever our n is. And we want to make sure that our energy remains constant. That means h evaluated at the initial point is equal to h evaluated at all points, which means that error of h evaluated at the initial point and h evaluated at all points, the error should be 0. That means the energy is conserved numerically as well. And for this purpose, in this talk, I will talk about symplectic Runge-Kutta methods because they approximately preserve the quadratic first integrals of Hamiltonian systems. And what we are trying to do is that we will construct from the definition symplectic Runge-Kutta methods, and then we will apply these methods on the Hamiltonian system, and then we will verify their order, and then we will verify the conservation of energy as well. Okay, so we are interested in a separable Hamiltonian system, and this is an equation of a separable Hamiltonian system in such. And we have extended this work to, and this work can be extended to non-separable Hamiltonian system as well. And so the equation one is a separable Hamiltonian system or differential equation in the sense that the P dash depends only on Q on the right hand side, and Q dash depends only on P. So this is a separable Hamiltonian system. And what we are trying to do is we are trying to solve this separable system using partition Runge-Kutta methods. When I say partition Runge-Kutta methods, I mean that I will solve one differential equation, which is P dash, using one Runge-Kutta method, which is given as the stages and the output value. Pi, capital Pi are the stages, and Pn plus 1 and Pn are the input-output values of one Runge-Kutta method, which is solving the differential equation P dash is equal to f of q. And the second differential equation Q dash is equal to G of P. This is the separable second differential equation, and we solve it using this another Runge-Kutta method, which with stages Qi and the output value Qn plus 1 with input value Qn. And we have over here the matrix Aij. This is the Runge-Kutta method for one, and the Bi are the quadrature weights for one Runge-Kutta method, and A tilde and B tilde, they are the parameters for another Runge-Kutta method. Nowadays, what we do is we write these Runge-Kutta methods just for the sake of presentation in terms of the Butcher table. So this is the Butcher table, and just a representation. It has nothing to do with the calculation, but it is a convenient way of writing any Runge-Kutta method. And we have the matrix A on the left hand side and A tilde. So just make sure that A, the matrix A is representing the RK method, which is solving the differential equation P, and the right-hand butcher table is with the tilde sign. This is solving the second differential equation Q dash is equal to P. Okay. Order conditions. When we want to find the order of a numerical method, or we want to find the order, what we do is normally in numerical analysis, we do is that we compare the numerical solution with the Taylor series of the exact solution. That is the rule to find the order of a particular numerical method. So if I have the Taylor series, if I have the numerical method Pn plus 1 and Qn plus 1, because Pn plus 1 is just one Runge-Kutta method and Qn plus 1 is the second Runge-Kutta method. And the Taylor series of the exact solution is y of xn plus h is y xn plus h y dash of xn. And we compare them, the numerical values and the exact solution, we will get order conditions. So we can see that there are 4 equations over here. The first 2 are the order 1 condition. That means if the Runge-Kutta method is of order 1, then this summation bi is equal to 1 and summation bi tilde is equal to 1. That means b1 plus b2 plus b3 is equal to 1, and b1 tilde plus b2 tilde plus b3 tilde is equal to 1. I think all of you are familiar with Runge-Kutta method of order 4 and order 5, classical explicit methods. They have 1/6 in the, in 1/6, 1/3, 1/3, and 1/6. So if you just add them together, they will become equal to 1. And the second bi ci tilde and bi tilde ci is equal to half. They are order 2 conditions. And we expand this Taylor series for high order, and then we can get higher order conditions as well. Order 3 is also possible, but order 4, order 5, order 6, up to let's say order 10, order 18, this becomes very difficult to find order conditions using this thing. So we use the concept of graph theory. So in this talk, I will talk about the relationship between the numerical analysis with the graph theory and the numerical analysis with the group theory as well. So we'll just go to graph theory. Just some basic definitions. In the graph, we consider a tree, which is given as T in the bottom. A tree is a connected non-cyclic graph. They have vertices and edges. Okay, so this black dots, they are vertices, and the joining lines, they are the edges. And we are considering the rooted tree. Rooted tree means that one particular vertex is considered as root. So it's just, if you just consider a tree in your garden, it has a root and it's going up. So just consider this tree like this. The bottom one is the root and it's going up. Order of tree, the number of vertices in the tree is the order of tree. So there are 4 vertices in it, so its order is 4. And then this density of tree. Well, density is very easy to calculate. The density, just count all of the vertices. They are 4. Write 4 for the root. Then remove the root. What is left? On the left hand side, you are left 1 vertex. Okay, so just put 1 over there. And on the right, you are left with 2 vertices. Just put 2 over there. And then go on and on. So 4 multiplied by 2 is 8. So that's the density of the tree. And we need this information actually. So these are the trees of up to order 4. The first order one and the second order has 2 vertices. The third order has 3 vertices. There are 3 possibilities. It's a rooted tree. So we just define the root at the middle point in the third. So we get a V-shaped tree. And if we put a root at the first point, it's a tall tree. So, and in order 4, we have four options over there, and they are order 4 rooted trees, and there are order 5 and order 6, all are available in literature. How can we use it in our differential equations? Well, this is very interesting. We have system of partition differential equation. P dash is equal to f of q. We just write it f. Q dash is equal to G of P, we write it G. We find the second derivative, P double dash, Q double dash, using, we find the third derivatives, which is F double dash GG plus F dash G dash F. This is using just a chain rule. If you just expand it using chain rule, you can easily get this thing. But what we can do is we can assign this F and G the trees, the vertices and edges. So every F and G is a vertex and derivative is an edge. I repeat again. Every F and G is a vertex. So because we have two F and G, so different. So F is a black vertex, G is a white vertex, and derivative is an edge. So F is a, if you see F dash G, F is a black vertex. Then we have a derivative, which is an edge. Then we have a G, which is a white vertex. Similarly, if we see this thing, G, the last one, G dash F dash G, G corresponds to white vertex. We have the derivative, then we have the edge, and then we have F, so it is a black vertex. Then we have a derivative, it's an edge, and then we have a G, it's a vertex white. So in this way, we can define we can relate the derivatives with the rooted trees. Okay. Okay, we can also relate the Runge-Kutta method coefficients with the trees as well. So these were the 4 order conditions of order 2. The first 2 are for the order 1 condition, and for the other 2 are order 2 conditions. We can say that, okay, so what we can say is a black vertex, we say it's BI. And white vertex, it's BI tilde. Remember, we have 2 Runge-Kutta methods. One is with the BI and one is with the BI tilde. Then if it is it's a connect, just one connection, black to white, we have BI CI, but CI is white vertex, so it's CI tilde actually. And similarly, so it's just, and then the last one, if you just look at the last one, which is BI tilde, AIJ, CJ tilde. So BI tilde is the white vertex, and then AIJ is the connecting black vertex, and CJ tilde is the white vertex. So it's a tall tree in the bottom of this page. So basically what we have done is we have related the trees with the derivatives of a differential equation, and we have related the trees with the coefficients of Runge-Kutta method as well. And in literature, this graph theory has been used extensively, using you can relate integration with the edges as well, and derivatives with the edges as well, and you can relate this the differential equations with the graphs and the integral equations with the graphs as well, and a lot of people are working on it. So if we compare the numerical solution with the Taylor series of exact solution, we found out that it's proved that these are the general conditions for order condition. The phi of t is equal to 1 over gamma of t. The phi of t is this over here. You can see this phi of t over here. These are known as elementary weights, summation bi, summation bi tilde, bi ci, and very beautifully it's 1 over the density of that particular tree. So you can see this thing. These are the 4 order conditions we have seen. So if it is just one vertex, is just bi is equal to 1 over 1, which is fine. And then bi ci tilde, and this is equal to 1 over the gamma of this tree, and the gamma of tree is 2, just 2. And the third one has gamma 3, and the last one has 6 because it's a 3 vertices over there. So we just assign 3 to the root, then we remove the root. The left are 2 vertices. So 3 into 2 into 1 is 6. So we can relate the trees with the and then we can now we don't need the Taylor series. We just need the trees to construct our order conditions. We just consider higher order trees and we define our order condition, and we solve those order conditions and we get the Runge-Kutta methods. These are order conditions for tilde trees. These are order conditions for non-tilde trees. Okay, now the concept of effective order. Well, for Runge-Kutta method of order 1, we require 1 stage. For Runge-Kutta method of order 2, we require 2 stages. For Runge-Kutta method of order 3, we require 3 stages. For Runge-Kutta method of order 4, which is known as the classical Runge-Kutta method, we require 4 stages. For Runge-Kutta method of order 5, we require 6 stages. So as the order increases, the number of stages increases. And in each stage, we calculate the function values, function valuation. And function valuations means right-hand side of the differential equation. So if it is a big system, like 100 by 100 differential equations, then it means that you are calculating F a lot of time. And this is a computational cost. And we want to decrease the computational cost. So in order to decrease the computational cost, what the people have done is that they have developed methods of the higher order with less number of stages, and these methods are known as the effective order methods. And idea is very simple. Just use we take the initial condition, why not? We take the first step with one RK method, calculate y1, and then we calculate y1 to yn with the second RK method. And this is a composition over here. So we have a composition over here. And when we have a composition, we have to make sure that this composition is well defined. So we have to go to the group theory, because in the group, if we have this composition rules over there. So I'll just quickly go over there as well. So the Runge-Kutta method U has an effective order P if we have another Runge-Kutta method V such that U, V, U inverse. So we have applied the U in the beginning. So we have to cancel this effect of U in the beginning by applying the U inverse. And if this Runge-Kutta method forms a group, then that means we have the inverse available over here. So, and then we have this exact flow from trees to real number. E of t is just 1 over t. It's the right hand side of the equations. And this is the idea of effective order, that we are in the left corner, we are given y naught. We apply the Runge-Kutta method V, and we take one step. Then we apply the Runge-Kutta method U, and we take all the steps. This is equivalent to applying exact solution flow and applying V at the end. To the exact flow, and then we compare the Taylor series with the exact solution, and we get the order HP plus 1. So order is P. So for the effective order partition Runge-Kutta methods, now we have already 2 Runge-Kutta methods. So we need to have the starting method for the left Runge-Kutta method, and we need a starting method for the Runge-Kutta method with the tilde sign, and we need the finishing methods, which are the inverse method for both of these methods. So basically we need S, M, S inverse, and S tilde, M tilde, and S tilde inverse, and both should have order P. And we can say their elementary weights, which are just the coefficients, Bi, Ci tilde, the summation of them we have just defined a little bit earlier. As for the starting method, for the main method M and M tilde, the elementary weights are alpha and alpha tilde, and for the starting method S and S tilde, the elementary weights are B and B tilde. So basically what we want to find is, we want to find beta alpha of t is equal to E beta of t, and beta tilde alpha of t is equal to E beta tilde of t. Okay, so these are the order conditions for the effective order methods. It's a composition. So we construct, this is the main gist, this is the main point of the talk, that we construct effective order 4 method with just 3 stages, which is not possible in the classical Runge-Kutta methods, because classical Runge-Kutta methods, order 4 methods require 4 stages. Remember, in every numerical analysis class, NA1, NA2, we just discussed Runge-Kutta RK4. RK4 means that it has K1, K2, K3, K4 stages, but we have constructed effective order 4 method with just 3 stages. And how we have done it? The most obvious feature of these methods is efficiency in terms of implementation cost. Okay, so we have to, because we are doing composition, so we have to define the composition. And basically what over here is that we have to make sure that Runge-Kutta methods form a group. So now it's the relationship of the numerical analysis with the group theory. So if a Runge-Kutta methods form a group, it has to be closed, the first thing. So it's a close for, so this means that if I take 2 Runge-Kutta methods, I compose them together, then I get another Runge-Kutta method. The answer should be another Runge-Kutta method. So I take first Runge-Kutta method. I calculate from y0 to y1 as one step, and then y1 to y2 is another Runge-Kutta method. I can combine them, and it's a big Runge-Kutta method over here. So going from y0 to y2 directly. And the butcher table for this one is this. So it's just a small a's, capital A's on the diagonal. On the off diagonals are zero matrix and B, and then the left hand side C's are the quadrature nodes, and we can obtain them using consistency condition. It's very straightforward. The sum of the rows should be C1, and these C1s are the points where we evaluate the stages. And then B1, B2 are the weights of the one Runge-Kutta method, and B1 tilde and capital B1 and capital B2 are the weights of the other Runge-Kutta methods. Okay, so we have composition in partition sense. So it's also well defined. Diagonals are A's and off diagonals is 0 and B tilde, and then the consistency condition. Composition in terms of trees as well. Well, so if we have this tree, so this is BI, CI, order condition of this tree is, okay, so the root is black, so it is BI, and then the other vertices are white, so CI tilde. There are three vertices, so C1, three vertices mean then there are C cube, so B1 C1 cube plus B2 C2 cube plus B3 C3 cube plus BI into CI plus BI cubes. And we expand them and we get it beta 5. These are the elementary weights.
Dr.
Plus,
Yusuf?
yes.
Sorry for interruption. You have only 2 minutes to please wind up your talk, please.
Just 2 minutes?
Yeah, it was supposed to finish at 10:35. Yes, so kindly try to wind up.
Okay, okay.
If
So
it is not possible yes. If it is not possible in 2 to 3 minutes, then you may take 5 minutes maximum, please.
Okay, no worries. Okay, we define the inverse as well, and inverse is also well defined. And basically, we solve these order conditions. These are the effective order conditions. If we solve them, we obtain this effective order partition methods. And you can, these are the order 3 method with just 2 stages. Then we have effective order 4 partition program with 3 stages, and this is very good achievement. And we verify the order. We these are the starting methods. We verify the order. We apply it on the Kepler's two-body problem, and this is the exact solution. We apply these methods, and this is a procedure given that we applied. And this table is important, that we can see that this is the standard technique to find the order of the method, and which means that we half the number of steps and double the number of steps and half the step size. And you can see the ratio is a global error. The ratio is 16, which is 2 raised to the 4. So its order is 4. So this verifies that our method has order 4. But now we want to solve, we want to derive the symplectic partition, effective order partition Runge-Kutta methods. That means that our partition Runge-Kutta method has to solve this additional differential equation. This is the symplectic condition for partition Runge-Kutta methods. And this is used to simplify our effective order conditions. And we solve them and we get effective order symplectic partition Runge-Kutta method. These are order 4 methods with just 3 stages. These are the starting methods. And now these are the main methods, and these are the starting methods. And we apply these methods. This is my last slide. So we apply this method on Kepler's problem, and you can see this symplectic method has been applied on a conservative Hamiltonian system, and this is the error in the energy. And on the x-axis is the time, and on the y-axis is the error in the energy. And you can see it is on the y-axis, it is 10 raised to the minus 11, which is approximately, which is actually 0. 10 raised to the minus 11 error is 0. So this shows that if we apply the symplectic method to solve a Hamiltonian system, we will get the conservation of energy. And we have also done the number of function evaluation details as well, but not part of this talk. But the number of function evaluation verifies that our computational cost is also less as compared to this, the standard classical methods. And this has been published. There are several papers related to this one. This has been published as well. Well, with this one, thank you very much for your time and for listening. Any questions?
So any question from the audience, please? Is there any question from the participants? So I guess there's no hand raised. So let us thank our speaker for a very interesting talk, Dr. Yusuf.
Thank you very
so
much.
much.
Thank you. Thank you very much.
So, can you please, yeah. Okay. So our next speaker is Dr. Sadia Hina from Fatma Jana Women University. She is the chairperson at the Department of Mathematical Sciences, Fatma Jana Women University, Rawalpindi. Her field of research is fluid mechanics, particularly peristaltic flows. The title of her talk is a novel formulation for MHD flow of elastico-viscous fluid induced by peristaltic waves with heat and mass transfer effects. So please try to wind up your talk. Yes, please try to wind up your talk in 20 minutes.
Okay.
Yeah.
Let me share my talk. It's visible?
Yeah, it's visible.
Thank you. First of all, I would like to thank the organizing team for their invitation. And I also congratulate them for organizing such event in this pandemic situation. Today I will talk about novel formulation for MHD slip flow of elastico-viscous fluid induced by peristaltic waves with heat mass transfer. The main key factors are as follows. Like an introduction, I'll talk about the main key factors like peristalsis, Walter-B fluid, heat mass transfer effects, and what is the main problem which we have considered. Then in mathematical representation, I'll talk about the main problem which we have formulated and the formulation of that formulation of the problem and how we solve that problem by using which technique and under which assumptions we have solved. Then we'll discuss the graphical results after obtaining the solution from mathematical problem technique. And at the end, I'll conclude my talk. Firstly, peristalsis is the form of fluid transport due to the wave traveling along the walls of the tube. It is basically the contraction of smooth muscles to propel the contents through the digestive tract, or this is in many biological processes, this phenomena occurs like the transport of urine from kidney to bladder, transport of food bolus through esophagus, transport of blood in small blood vessels. This phenomena also occurs in motion of blood through different blood vessels. And this is occur in many biological, in industry like pumping different fluids like toxic fluids in industry. And this phenomena was firstly discussed by Latham in 1966 in his MS thesis. The main discussion is the Walter-B fluid in peristalsis as different fluids appearing. Yes.
Sorry for interruption, but can you please fix your mic a little bit? There is a little distortion from your end. So.
Okay. Walter-B fluid is a class of viscoelastic fluids that non-Newtonian fluid is already explained very much by dear colleague Dr. Sajid, who have explained in a very detail. about non-Newtonian fluids. Walter B. fluid is the subclass of viscoelastic fluids that describes the elasticity and viscous effects, and like nylon, jelly, paints, and many biological fluids like blood is also considered as viscoelastic fluid. Walter B. fluid was first introduced by Walter in 1964, and many authors have done a lot of research about Walter B. fluid by considering many industrial problems as well as in peristalsis. Uh, then I have considered the slip condition. The main slip condition we have considered slip condition because the boundary is in that case the fluid at the boundary and the wall both have not the same velocity. At that time we have considered the slip condition, that the velocity of the fluid is not directly proportional to the velocity of the wall. So at that time, we have considered the difference between fluid velocity and the velocity of the wall as proportional to the shear stress. At that time, we have considered the slip condition. And this phenomena occurs in many problems like artificial polishing of artificial hard walls and in internal cavities. That's why we have considered the slip condition in peristalsis and with Walter B. fluid. As this phenomena in peristalsis was firstly discussed by Chip and Fang in 2000 in peristalsis. Then we have considered heat and mass transfer effects in the present study as well. As heat transfer is the transfer of heat from high temperature region to a low temperature region, and it have a lot of applications like conduction in tissues, heat convection due to the blood flow through the pores of the tissues, and radiation between surface and its environment. This phenomena occurs in blood flows in hemodialysis on the oxygenation process. Then mass transfer effect, this is the transfer of mass from high concentration region to the lower concentration region. This phenomena occurs in filtration, drying, evaporation, etc. As peristalsis with the heat and mass transfer effect is very much important in medical operations like mass transport in blood oxygenation process and hemodialysis. Heat transfer in peristalsis was firstly discussed by Radhakrishna Mishra and Srinivasan in 2007. Uh, uh, Using all the above mentioned things, we have formulated the problem with the condition that we have considered the incompressible fluid, viscoelastic Walter B fluid with slip conditions, and we have considered the peristaltic motion, which is due to the sinusoidal waves traveling along the walls, and considered the heat and mass transfer effects. This is the main geometry of the problem, that the fluid is flowing between the channel, and the channel width is 2d. Here the waves are traveling along the walls, and the wave amplitude is a. The wave length is lambda, and the wave speed is c. So here the geometry of the wave is defined as y, which is the upper wave is y is equal to eta, and the lower wall is y is equal to minus eta, that the sinusoidal waves are traveling along the channel walls. This is the main stress tensor, which is not discussed before, as many authors have already discussed that. Many authors discuss the peristaltic motion for Walter B fluid, but there is a little mistake in that studies, like they missed the 1/2 in strain rate tensor, and also defined the wrong upper convected time derivative, due to which the shear stresses obtained in that articles are not correct. So we have considered the correct formulation, as 2 is the equation represents the shear stress for Walter B fluid, where eta naught is the dynamic viscosity, and K naught is the Walter B fluid parameter. And here E is the shear rate tensor. D by dt describes the upper convected time derivative. So we have considered the corrected formulation which was discussed by Walter in 1964 and Barris in 2002. The correct stress tensor can be seen in the articles presented in 5 and 6. These are the governing equations of the problem, as the first main equation we have considered in fluid mechanics is the continuity equation. Then we go for the momentum equation. So 5 and 6 are the x and y component of momentum equation, as we have considered a two-directional flow. U is the velocity along the axial direction, and v is the velocity in the transverse direction, and they are depending upon x, y, and t. Here, equation 7 is the energy equation, which involved the viscous dissipation effects, which is described in equation 8. We have considered the viscous dissipation effect here, and equation 9 represents the concentration equation, as we have considered the mass transfer effect as well. And here, concentration flux, mass flux is also generated from the temperature gradient, which is represented in equation 9, and the last term represents that the concentration mass flux is generated due to the temperature gradient, which is the Soret effect, which we have considered in equation 9. These are the stress components which are derived from the correct variant mentioned in equation 1, equation 2 and 3. These are the stress components Sxx, Sxy, and Syy. These are the required stress tensors which we will use in our momentum equations. The problem is in the laboratory frame, so I would like to transform the laboratory frame to the wave frame. That's why we have considered the transformation. And using this transformation, we transform our problem from laboratory frame to the wave frame. So after conversion, we are free from time derivative, and these are the equations after using transformation. These are the equations from 14 to 22, including stress components, viscous dissipation term, energy and concentration equations. These are in the form of wave. These are defined in wave frame now. Now we consider the problem is highly nonlinear and dimensionless, and so we would like to dimension less first this problem, and for that we will consider the dimensionless quantities as x, y's, velocities, times, and so on. We will dimensionless the problem, and after non-dimensionalization, the problem involves some non-dimensional parameters which are described in the last two equations, like delta is the wave number, epsilon wave amplitude, Reynolds number, Eckert number, Smith number, Hartmann number, Frickman number, etc. These are the parameters appearing in the non-dimensional equations. These are the non-dimensional equations presented from 23 to 30, where 23 and 24 are the x and y component of momentum equation after introduction of a string function in the x and y component of momentum equation. 26 is the 26 is the concentration viscous dissipation term. 27 is the concentration equation. Here by mistake 25 is not the energy equation. Sorry for that. 28 to 30 are the stress components. These are the boundary conditions now. We have initially was discussed that we have considered the slip effects. Here equation 31, which is the boundary condition we have seen here, psi is f by 2 plus minus f by 2 at plus minus eta, which describes the flow rate along the channel. And the second condition represents the velocity slip, where beta 1 is the velocity slip parameter, that the velocity plus minus is shear stress with the slip parameter, which we have already discussed, that the slip, the fluid at the wall with minus fluid at the of the fluid velocity of the fluid, and the velocity of the wall is proportional to the shear stress, which is represented in 31B. And equation 31C and D are the concentration and temperature concentration slips, as beta 2 and beta 3 are the thermal slip parameter and concentration slip parameter. And non-dimensional geometry is defined as y is equals to plus minus eta. As the problem we can see here is highly non-linear, and the boundary conditions are also non-linear due to the shear stress appearing in the boundary condition as xy. As we can see that SXY is highly non-linear, and we also are not using the long wavelength low Reynolds number approximation in the problem, because if we apply the long wavelength and low Reynolds number approximation, the problem will be reduced into the Newtonian fluid. So we are not applying that assumption. And if we cannot apply that assumption, so our problem is highly nonlinear. So what will we do? We can solve it by a regular perturbation technique. We have solved the problem by regular perturbation technique about small wave number, as wave number is very small because it is the ratio of the wave amplitude to the wavelength, and wavelength is very large, due to which the wave number is very small. We have considered the small perturbation, regular perturbation technique about small wave number. By applying these assumptions and of regular perturbation technique presented in 32 into our problem from 22 to 23 to 30, we compare the term of delta naught, like the zeroth order system. We obtain the zeroth order system, which is we can see that this is the form of OD, so we can solve it easily, the zeroth order system. Then we got the solution equation of first order system, like comparing the equation of delta 1. As these are the equations for first order system, we can see in equation 34 by comparing the coefficients of delta power 1. Here the forcing terms are a lot of psi naughts are appearing in the forcing terms, so it is highly complicated equations. We can use D-solve, but that was very complicated in Mathematica, so we solved them by hand. After finding the solution of zeroth and first order solution, we combine the solutions and we obtain the stream function, velocity profiles, axial velocity, temperature, concentration, and heat transfer coefficients. After that, we go for graphical results, that how different parameters behave and how different parameters affect our velocity, temperature, concentrations, and heat transfer coefficient. So the behavior of different parameters can be observed through graphs. As we can see that the velocity profile is parabolic nature, which means this is the Poisson flow at because the peristalsis is due to the pressure gradient, and due to which this is like the curves are the velocity is maximum in the center as compared to the walls, and at the walls the velocity is almost zero. That's why we got such type of profiles. As from figure 1 and 2, we can see the behaviors of viscoelastic Walter B fluid parameter and the Hartmann number, which is due to the consideration of MHD effects. And we can observe that both have opposite behaviors. First one figure shows that the curve for K is equals to 0 is for Newtonian fluid, whereas the curve in the red color for K is equals to 3 is for the viscoelastic parameter. From 1 to 3, all are for the viscoelastic parameter. But we can observe from here that the velocity for Newtonian fluid is smaller than the velocity profiles for velocity for Walter B fluid. So Walter B fluid parameter enhances the fluid velocity. Then in Hartmann number, we can see that the magnetic field is in the transverse direction, which drag the axial velocity or axial motion. So due to which the velocity profile is decreasing with the Hartmann number. So by increasing Hartmann number, the velocity is decreasing. These are the graphs of temperature profiles. As we have, it is the main thing that why the curves are like this, as the lower wall have temperature 0 and the upper wall have temperature 1. So why the temperature rise in the channel? This is because of the consideration of viscous dissipation effects, that the viscosity affects the temperature. So here we can observe that viscosity parameter enhances the temperature, that it increase the temperature for viscous dissipation. So these are the graphs for temperature, as the figure 3 is for Hartmann number, figure 4 is the thermal slip parameter. As we can see that Hartmann number decreases the temperature, as most of the parameters have the same behavior on velocity and temperature. As the velocity increases for different parameters, is the same case that temperature increases for that parameters. And here the thermal slip shows that for 0 slip, if we does not consider the slip effects, no jump condition, then the velocity temperature is less as compared to the jump condition. We have considered the temperature jump condition. So beta 2 enhances the temperature. These are the plots for concentration profiles. Concentration is somehow the inverse of temperature. So different parameters that enhances the temperature will reduces the concentration profiles. Here BR is the Brickman number, which is due to the viscous dissipation effects. BR enhances the temperature, and on concentration, it will decrease the concentration. And beta 3 is the concentration slip, which shows that the concentration for no slip case is higher as compared to the concentration for concentration is smaller for concentration slip parameter. These are the heat transfer coefficients, graph of heat transfer coefficient, which is the rate of heat transfer. As we can see that these are of oscillatory nature, and we observe the absolute value of heat transfer coefficient here. So the thermal slip parameter enhances the heat transfer coefficient, and it reduces the Hartmann number. Heat transfer coefficient, Hartmann number reduces the heat transfer coefficient profiles. These are the streamlines. Basically, streamlines describes the flow pattern, that the wall is the shape of the walls, and these are lines that describes the flow pattern. But some lines split and form the circular shape, which is called as the bolus. And most of the time we discuss the bolus size and trapping bolus, number of boluses in the streamlines. As here we can observe that the slip parameter reduces the size of trapped bolus. As from figure A, we can see that the size of trapped bolus is larger as compared to the figure C. The right hand side, this figure represents that the size of trapped bolus is small as compared to the size of trapped bolus present in the figure A. So here slip parameter reduces the size of trapped bolus. Hartmann number have the same behavior like slip parameter on stream function, streamlines, like the size of trapped bolus decreases with the Hartmann number, that the size of trapped bolus is larger in the first one case as compared to in the last case, where the size of trapped bolus is very small as compared to the figure A. These are the pressure rise. Here we can see that this region represents the peristaltic pumping, and this region represents the augmented pumping region. As a pressure rise, we have discussed that it can be observed that pressure rise is increases with the Hartmann number in peristaltic pumping, whereas it decreases in the augmented pumping with Hartmann number. And same is the case that pressurized decreases in peristaltic pumping, and it increases in the augmented pumping with beta 1 slip parameter. At the end, I'll conclude my talk as we have considered the this formulation. We have considered the Walter B problem as its formulation was not correct, firstly discussed by different authors. So my main theme was to formulate the correct variant of the Walter B fluid model in peristalsis. And we have considered the sinusoidal waves in a symmetric channel. The main key observations are as follows, like axial velocity is higher for or increases with the viscoelastic fluid parameter as compared to the Newtonian fluid, and the profiles are parabolic, as we have already discussed that it is the sort of Poiseuille flow, because the flow is due to the pressure gradient, and temperature profiles are parabolic in the study because of the presence of viscous dissipation effects. And pressure rise, we can see that the temperature rises by increasing viscoelastic fluid parameter. This paper is published in Arabian Journal for Science and Engineering. If anyone interested can see from Science Direct. Thank you. Any question?
Thank you very much, Dr. Hina. Questions are welcome from the audience, from the participants. So, yeah, kindly raise your hand if anybody is interested to ask questions. So I guess there is no question since there is no hand raise. So let us thank our speaker. Yes,
Thank
please. Okay,
Thank
so
you for your invitation.
Let us thank our speaker for such a nice talk. Thank you, Dr. Sadia. Now, we have the final talk of this first session, and I would request Mr. Mohammed Yahya to please share his screen. He will be speaking on Frank aggregation operators and their application to interval valued probabilistic hesitant fuzzy multiple attribute decision making. So it was a very difficult title. May I request Mr. Mohammed Yahya to please share his screen and proceed with the presentation.
Mr. Muhammad Yahya, not Muhammad Rais. You can give.
I trust that these are the presentation slides of Mr. Reis, not from Mr. Mohammed Yahya. Mr. Mohammed Yahya, if you can hear us.
Hello.
Yes, Mr. Yahya. Can you please share your screen?
I'm sharing. Yes, I am sharing, sir. A minute. This was not. Again, I'm sharing 1 second. So I'm very thankful to the organizer to provide such platform to talk a few minutes in front of dear professors. So my presentation is about rank aggregation operator and their application to the interval value probabilistic hesitant fuzzy aggregation operator. The layout of my presentation is about abstracts, and there are some basic concepts, research methodology, as well as there are application. We have to compare y numerical example and some comparison section with other existing methods, and in the last there are conclusion, and some references are also drawn in the last. So my talk there is abstracts is about the fuzzy aggregation information play an important role in the group decision making under the interval value probabilistic hesitant fuzzy information. Therefore, in this talk, we develop a new approach of the interval value probabilistic hesitant fuzzy aggregation operator based on Frank T norm and T conorm. First, we have defined some operational law on of interval value probabilistic hesitant fuzzy elements by using Frank T norm and T conorm. Further, we have developed a series of interval fuzzy aggregation operator which is also based on interval value probabilistic hesitant fuzzy information. Also, further, we have discussed some aggregation operator and algorithm. Then which next we have to apply on these practical decision making problem. And in the last, we have some comparison section we have to show as a by mathematical form. So in this drug there are some basic concept or about fuzzy set. What is fuzzy set? Fuzzy set, let x be a packed sets. A fuzzy set can be defined as this, is given as equation, where mu of x show the membership degree, and also this membership degree contained to the closed interval 0 and 1. Next is about interval value fuzzy set. XBFX set, then the interval value fuzzy set can be defined as follows, where the closed interval show us the lower values as well as the upper value can be represented by mu of x positive and mu of x negative respectively. And also these interval value contain to the closed interval 0 and 1. Next definition is about hesitant fuzzy set. That what this is hesitant fuzzy set. So hesitant fuzzy set can be defined as, let S be a fixed set, and hesitant fuzzy set can be defined as follow, where h of x show the possible value in the closed interval 0 and 1. Next is about interval value hesitant fuzzy set. Interval value hesitant fuzzy set can be represented as by the equation where h of dash of x show the possible membership grading belonging to the closed interval 0 and 1. And also there are sub interval where sigma of negative and sigma of positive show the upper value as well as the lower value of the intervals, which is also called interval value hesitant fuzzy elements. Next is about probabilistic hesitant fuzzy set. Let x be a fixed set, then a probabilistic hesitant fuzzy set can be represented as equation where h of x show the possible grading as well as p of I show the probability of that hesitant fuzzy elements. Next definition is about interval value probabilistic hesitant fuzzy sets. The probabilist interval value probabilistic hesitant fuzzy can be represented as an equation where h of dash x show the possible grading memberships, and also pi show the pi show the probability, but here we have to provide an interval value. Next is about interval value probabilistic hesitant fuzzy set and their basic properties. So these are the basic properties for the interval value probabilistic hesitant fuzzy sets. Frank operational law for interval value hesitant fuzzy set can be represented as follows, where equation 1 show the addition of two interval value probabilistic hesitant fuzzy set. Equation 2 provide the multiplication of any two interval value probabilistic hesitant fuzzy set. And the third one is about the scalar multiplication of interval value probabilistic hesitant fuzzy set. The fourth one is about the power multiplication of any two interval value probabilistic hesitant fuzzy sets. Next is about we have to develop which is based on interval operators. So which is the interval value? The Frank is about let Kj be the collection of interval value probabilistic hesitant fuzzy elements. Then the Frank order weighted averaging operator can be represented as follows. Next is about interval value probabilistic hesitant fuzzy hybrid weighted averaging operators. Let Kj be the collection of interval value probabilistic hesitant fuzzy element, and Pi or Ki is the interval value probability. Then the Prang hybrid weighted averaging operator can be defined as follows. Next is about interval value probabilistic hesitant fuzzy weighted geometric aggregation operators. So let Kj be the collection of interval value probabilistic hesitant fuzzy element, and Pi and comma Ki are the interval value probability. Then the Frank weighted geometric operator can be defined as this. Next is about interval value probabilistic hesitant fuzzy order weighted geometric operator. Let Kj be the collection of interval value probabilistic hesitant fuzzy elements. Then the Frank order weighted geometric operator can be represented as this, where K Pi and Ki the interval value probability. And next is about interval value probabilistic hesitant fuzzy Frank hybrid weighted geometric operator. Let Kj be the collection of interval value probabilistic hesitant fuzzy elements. Then the Frank or hybrid weighted geometric operator can be represented as follows. Next is about multi-attribute decision-making approach based on Frank operator. In this section, we have a collection of alternatives as well as weights, and the summation of weight must be equal to 1. Let Further, we have a collection of decision matrix containing the attribute as well as alternative. Next, we have to define to propose our methodology, which contains some steps. Step 1 is about to transform the decision matrix into normalized matrix. Step 2 is about using the proposed aggregation operator, which is interval value probabilistic hesitant fuzzy Frank hybrid averaging, or interval value probabilistic hesitant fuzzy Frank weighted geometric operator to aggregate the information. Step 3 is about to find the score function of all aggregated matrix. Step 4 is about rank the aggregated alternative according to the higher value of score function. So this was our proposed methodology, which contain some of steps. Now we have to implement on practical examples. Application and decision making problems. This was a numerical example which we have to apply or propose aggregation operators. Sale managers want to fill the empty positions in a company. In a company, there are 6 alternatives or candidates, which is represented by this. By using the 4 attribute, we can make a decision. They have the following setup. The C1 is represented as skill communication. C2 represent the past work or experience. C3 represent the aptitude of the candidates. C4 is about the self-confidence of the candidate. Here we have also a weight vector, which is represented as this equation 0.35, 0.25, and 0.15. Now to apply the proposed aggregation operator to evaluate the best alternative, and in this example we have to find the best alternative, the best candidate for this company. We have to apply using the interval value probabilistic Hessian fuzzy aggregation operator, which is about next slides. This was the data we have to draw for the selection of alternatives. So this data type of is interval value probabilistic Hessian fuzzy sets. This was the data. Now we have to implement or propose aggregation operator. Step one is about normalization. So in this data there is no steps one, no need of step one, because the data is of normalized form. Step two is about by applying the interval value probabilistic Hessian fuzzy Frank hybrid geometric operator, and also the weight vector arguments. So we have to apply it. Step three is about uh, to find the score value of aggregated uh, alternative, which is given as follows. Score function is about of a1, alternative 1 is this, alternative 2, alternative 3, which are given as this ways. So according to the score value, the ranking of the alternative is follows. According to the score value, we have ranked the alternative in which we have given as a3 is best, a4 is best. From the step 3 we have seen that the value of a3 is 0.314. Next is about a5, which is 0.2. Next is 0.4, 0.19, sorry. Next is 0.1115, and in the last 0.024. So this was the numerical example, and we have applied this proposed irrigation operator, and the last they provide us the best ranking alternatives, which is a3. The next is about comparison with other methods. Now we have to compare our method with existing methods. The above example is solved by using the proposed aggregation operator, namely interval value probabilistic Hessian fuzzy aggregation operator, fuzzy Frank hybrid geometric, sorry, interval value probabilistic Hessian fuzzy Frank hybrid averaging. Through this, we found that A3 is the best choice for the investment company. Now, the comparison analysis is made with the existing aggregation operator, which is Hessian fuzzy Frank Hamacher aggregation, Hessian fuzzy Einstein Hamacher aggregation operator, and Hessian fuzzy Hamacher hybrid averaging operators, and we obtained the same best alternative. Hence we conclude that our proposed method is applicable and more reliable to tackle the uncertainty in decision making problems. So this was the comparison with other existing method that we have also developed our proposed method, but in these slides we have to compare our proposed method with other previous existing methods. So from these tables we can see that all of these ranking method are the same, which is A3. The ranking results of proposed and existing operators are as follows. So in this talk, we have provide a new decision aid approach inspired by the classical fuzzy structure to develop a multi-criteria decision-making problem under interval value probabilistic Hessian fuzzy and interval value Hessian fuzzy environment respectively. As the aggregation operator play an important and crucial role to aggregate the real-life uncertainty in decision aid problem. Thus, in this talk, we established the list of aggregation operator to tackle the uncertainty in the form of interval value probabilistic Hessian fuzzy set as well as interval value Hessian fuzzy set respectively. The developed aggregation operator are based on a algebraic and Frank T norm. The established aggregation operator, namely interval value Hessian fuzzy Frank weighted averaging, order weighted averaging, and hybrid average weighted averaging, as well as we have also developed interval value probabilistic Hessian fuzzy weighted geometric, order weighted, and hybrid weighted geometrics aggregation operator. Now in the last there are some references we have done, and this was thank you for such a nice.
Okay, so house is open for the question answers, please.
Good question.
So participants are encouraged to ask any questions.
Yeah.
So if there is no question, let's thank our speaker for a nice talk.
Thank you, Dr. Saab.
Yes. Moreover, I would like to say that this was the final talk of the first session. Now we are going to have a break, and
Yes.
break of only 6 minutes. We will be joining by 11:30 for the second session of the second day, and so I would request you to please proceed for the break and join by 11:30. Thank you very much for your attention.